Hello, welcome to an episode of The Naked Scientists recorded live at the Cambridge Science Centre. Welcome, everybody! It's great to see so many people here. And what we're going to talk about this week is extreme geology. Now, extreme means way beyond the normal. There are extreme geologists, as we have with us this evening. There are also extremophiles. These are things that can love and tolerate extreme environments, rather like the crowd at a Justin Bieber concert. We're not going to talk about extremophiles so much as what Mother Nature does by way of extremes this week. And we have with us an amazing panel of scientists from Cambridge University. I'm going to introduce you to them. Please welcome Professor James Jackson, Tanuka Ilanko, and Arwen Deuce. If I could ask each of you in turn just to tell everybody a little bit about yourself and what you do. James, go first, please.
I study big earthquakes and see what happens in them. There have been a lot in the news the last few years, if you've noticed. And the reason we're interested in what happens in big earthquakes is that you can learn from them. You can learn something about how the planet works, which we live on, but also if you understand what goes on in them, you can prepare for them. We can't stop them happening, but we can try and prepare for them so that they don't cause quite as much damage as they would otherwise.
Tanuka.
I'm a volcanologist and I work with volcanic gases. Now, I think a lot of people think of volcanoes as something that just erupts really hot molten rock, but what's actually behind that is the gases that are dissolved inside. And I work at Erebus Volcano in Antarctica, measuring those gases, trying to find out what's going on inside the volcano to make it work.
Do you have to have a particular penchant for the smell of rotten eggs to do that job?
Maybe. You do come to love it if you don't before you start.
The volcanoes are quite smelly as well, aren't they? Arwen, welcome.
I'm a global seismologist and I'm interested in earthquakes, just like James, but for a different reason. I like to use these earthquakes to make pictures of what the deeper part of the Earth looks like. The seismic waves are the only way to see through the Earth. There are eyes to make the pictures of the Earth. And it's similar to making a brain scan. You're probably used to seeing the pictures with the nice colours, the red and the blues, and those pictures we make of the Earth.
So get your thinking caps on, because we'll be talking to each of these people and we will be giving you the opportunity to ask them some questions. Interspersed amongst them, we'll be doing some experiments this week. And Dave and Ginny are standing by in our kitchen science corner. What have you guys got for us, Ginny?
So we're going to be doing a tornado, which is a type of sort of extreme weather, but we're going to be making ours out of fire rather than out of wind.
We're also going to be trying to build a model of a volcano, but a small one, so it shouldn't be too big.
Just a mini volcano. And then we're going to be looking at acids, because we're going to be talking a little bit about acid rain, which is something that can happen after volcanic eruptions, which I'm sure Tanuka will tell us about a bit later.
So, James, tell us about what actually happened in Japan. There was this huge tsunami that surged in. Tell us a bit about tsunamis and how they tend to happen.
The sort of tsunami we're talking about followed big earthquakes. And the tsunami which followed the big Japan earthquake was much bigger than people anticipated. And this was extremely interesting to us. The Japan earthquake itself was huge. It was one of the 4 or 5 biggest earthquakes of the last 100 years. But even the biggest earthquakes, we think we can anticipate the size of the tsunami which goes with them. But in this particular case, it was much bigger. And that's what caused the trouble. It drowned lots of people because the tsunami was a bigger wave than we thought it was going to be. And it also, of course, caused the damage to the nuclear power station at Fukushima. So trying to understand the connection between the earthquakes and the tsunamis is very important. And trying to understand what happened to make that one so special is also something we need to understand in order to plan for it in the future.
What did happen?
Well, you have to understand what happens when earthquakes happen. Earthquakes happen when rocks break and they slide past each other. And as they slide past each other, these rocks, on a surface, you can imagine a knife cut in the earth, and the rocks slide past each other, rather like rubbing 2 bricks together. The vibrations make sound, the sound travels through the earth, the sound shakes buildings. That's what normally causes the damage. But what you also do is move the rocks past each other. And if you move them past each other on the seabed, the sea has to get out of the way. You can't just change the shape of the sea bottom without the water going somewhere. And that's what makes the wave at the surface. The wave at the surface in this case was very big because the seabed moved a lot more than we thought it ever could.
How much?
In this case, in Japan, the seabed itself moved up to 50 meters. To put that in perspective, 50 meters is twice the length of a big swimming pool. And that's a huge amount to move in one go. We didn't think it was possible. The way earthquakes happen is that although the rocks will slide past each other on this surface, the surface is held together by friction. And so as you push harder and harder and harder, the rocks bend like a spring until eventually they can't bend anymore and they go twang and they move. But you try bending rocks 50 meters. It's a lot to bend a rock. And that was the surprise. We've seen earthquakes which have moved 10, even maybe 20 meters before in one go, but 50 was a lot more than anyone thought was possible. And so once we realized, and there were clever ways of measuring how much had moved, that was another special feature about Japan, that the Japanese are very, very good at observing what happens. We had fantastic information, and it was quite clear that this movement was as much as 50 meters. At that point, it was clear that there was something going on which we didn't understand. And it wasn't the only earthquake which has done this. There have been at least half a dozen earthquakes in the last 50 years, which were also puzzles in this sense.
How did you try and find out what had caused it?
Something had happened to all of these earthquakes which had made the tsunamis bigger than they should have been. And so what we had to do to find out what caused it was find out why the seabed had moved so much. You can't really store 50 meters in rocks, and it was clear something else had happened. What had actually happened was that although the rocks had moved, they moved in a particular way. The easiest way for you to imagine this is if you imagine a triangular wedge of wood on the floor, and if you tread on it, it shoots forward a lot. So you don't have to tread on it much, and then it will shoot forward a great deal. And that's the extra effect which happened in Japan. So we discovered that by looking very closely at what the seabed looked like afterwards.
Got a question here, and we'll be taking questions from you in a second. So if you have any questions about earthquakes in general or specifically Japan, get ready to put your hands up. But I've got a question here from John Burkitt by email, chris@thenakedscientist.com, James. And he says, how has the earthquake in Japan affected the rest of the world? Because there were some claims going around that it sort of knocked the Earth a bit off kilter in the way it rotates and that kind of thing. Is that true?
Yes, the length of the fault, the break which moved, was about 400 kilometers. It moved up to 50 meters. That's moving around a lot of rock. It actually does change the shape of the Earth. It affects the orbits of satellites, and we can measure all these things. And the vibrations, as Arwen will probably tell you, if you hit the Earth with something that big, it vibrates like a gong for something like 6 months afterwards, and we can measure that too.
And you can see the waves bouncing around, can you?
You can measure them, not see them, but you can actually measure them with modern equipment, yeah.
Questions from the audience? Put your hands up if you would like to ask anything about earthquakes.
I'm Ewan from St Neots, and my question is about earthquakes and tsunamis. When an earthquake hits, the tsunami comes up. How far the distance of the tsunami wave can go before it collapses on itself?
That's a good question. What happens is you make a wave because you move the seabed, and that wave can keep its shape and it can travel all the way around the world. So the wave, which started off in Japan, could cross the Pacific, it could enter the Atlantic Ocean, even reaches up here. By the time it gets here, it's smaller, but it still has the same shape. It takes about 30 hours to get here from Japan. It will travel about the speed of a jumbo jet. And it's quite small. If you're in the middle of the ocean when this thing went past, it's only about 1 meter high, and it's about 300 kilometers in the length, the wavelength of this wave. And you wouldn't notice it. If you were in the middle of the ocean on a flat, calm day, you wouldn't see it. What happens, though, what causes the problem, is it slows up when it reaches the shallow water of the coastline. And because it slows up, the water piles up and up and up and up. And by the time it hits the coast, it may be 40 meters high.
Over here.
Yes, my name is Fergal, and I'm from Cambridge. I was wondering, how does the depth to the source of the earthquake influence the size of the resulting tsunami?
Only that the deeper it is, the less it will move the seabed. So what you heard about on the news quite a bit at the time of the Japan earthquake is that the fault which moved, the break between the rocks, came all the way to the seabed and upset it a lot. It moved the seabed much more than it might otherwise have done. If the fault doesn't come to the surface, it's rather like taking a telephone directory. If you move the top over the bottom, because of the binding, it will turn into a fold, which is much less dramatic than if it just breaks altogether.
Hi there, my name's Mark, I'm from St Neots, and I was just wondering how much rock type affects how this works.
That's an excellent question. A very large amount. And one of the problems in Japan is although the surface of the seabed moved 50 meters, it was mud. And mud has no strength. How can you possibly bend mud 50 meters? You can't do it, you know it. You can just about imagine that a really strong rock you can bend a bit, but soft mud you can't. And that's why we realized there must be some other process going on which we didn't know about and didn't understand.
Tanuka, do you see volcanoes getting triggered by earthquakes?
I think that's still an area that people aren't quite sure of. We do get earthquakes on volcanoes, which are related either to the rocks fracturing as gas and magma moves up through the volcano, or you might also get earthquakes that are from just the fluid moving itself. And these earthquakes are usually a lot smaller.
And Arwen, the waves that James is talking about ricocheting around the planet, they must give scientists like you quite a good insight into what's inside the Earth, because you can sort of use that data, can't you, when something big happens?
Yes, that's right. What you have, and you need a big earthquake for it, like the one in Japan. The whole Earth will ring like a bell. It's a bit like a musical instrument. Say you hit a drum, then there's a certain tone coming off it. And what we seismologists can do, we can listen to these tones. And for the Earth, they go on for a long time. They can go on for weeks, but for a big earthquake like the one in Japan, they can go on for months. And we listen to these different tones. And if the Earth was very simple and didn't have things like plate tectonics and volcanoes, then the Earth would be perfectly in tune. But what we find is the Earth sounds slightly out of tune. And we can listen to that, and that will tell us about the deeper parts of the Earth.
Hello, I'm Brendan from Cambridge. I wonder, are you familiar with the theory that a lot of very big earthquakes in the last decade are sort of linked and, whilst not aftershocks of each other, are sort of caused by each other and lead on from each other?
So can one earthquake beget another earthquake?
Yes, a lot of people are thinking about this at the moment. If you look at the biggest earthquakes of the last 100 years, about 5 of them have happened in the last decade. You would have said the same had you been around in the 1950s. And you do get this clustering of big earthquakes, and it's hard to tell whether it's really random or not based on statistics. There may be good reasons why one big earthquake can trigger another. If you actually shake the rocks around, you move things around, that may be the last tiny bit of effect you need to actually make some other fault slip in a different part of the planet. It's not impossible. It's rather difficult to prove, but we do know that one earthquake can trigger another one from the activity that you see actually around volcanoes very often. That after a big earthquake, little earthquakes around volcanoes very often increase in frequency a lot. And that's probably because you're knocking fluids which are sitting around in the earth and making them move.
My name's Jess from St Ives. During this last century, have the regularity of earthquakes increased and the size of them increased, or has it just been because we've been collecting more data?
No, there's no sign that the earth has changed its behaviour. There's a lot of sign that we have changed our behaviour. So earthquakes in the last century have killed far more than earthquakes in all the previous 1,000 years put together. And that's because we concentrate cities in dangerous places. About half the world now lives in major cities, and many of those cities are places that have been destroyed in the past. But in the past, it was quite difficult to kill even 10,000 people. Now we routinely kill 100,000 people in these big earthquakes in major cities in dangerous places.
James Jackson, thank you very much. Okay, time to get experimental. Ginny.
So we've been talking about earthquakes and tsunamis, but there are other kinds of events that are more related to weather rather than directly to what's going on under the ground. And today we're going to look at one of them. So what are we going to do?
So what we're going to do is try and actually build a model of hurricane, which is quite difficult in this smaller space. But what drives a hurricane is hot water heating up the air above it. You get hot, damp air above the water, and then that moves on. So we need a way of injecting energy into the system.
So when you heat something, it becomes less dense and it rises. So that's what happens to the water as it heats up. It starts rising. Now, we're not going to use water here. We thought that would be a bit boring. We're going to use fire. We're just going to set fire to some fuel here. And you'll see that you get a flame that should go upwards. The air's heating up and it's rising and it's expanding. And once we actually manage to set fire to it, you should see that. Hopefully it'll catch in a minute. And that's the same as what happens with the water. It gets warm and it starts to rise. Now, that's not a problem. You've just got something rising. When it becomes a hurricane is when it starts spinning. Now, the reason that happens is because over the oceans, winds can come in from a really far distance because it's flat, there's nothing to stop them. And the Earth's curved, so as these winds come in, they're actually spinning very, very gently because the Earth's spinning. Now, I don't know how many of you have ever watched ballet or ice skating. Anyone? Yeah? Have you ever seen it where the dancers, beautifully demonstrated by Dave here, he's an expert dancer, they start to spin, and they start out spinning quite slowly, and they've usually got either their leg or their arm out. So they're spinning quite slowly, and then all of a sudden they whip their leg in, and they suddenly go much, much faster. Have you seen that before? Who liked the demonstration? So that's happening because of something called the conservation of angular momentum.
So there's a couple of effects going on. One of them is that if you imagine going around a big circle and a small circle, the small circle's a lot smaller, so it takes you less time to get round, so you spin faster. And also, as you pull in, you're actually doing work. If you ever tried to climb into the middle of a roundabout, it's really hard work, and that work is actually going into speeding you up. So as you move weight into the centre, you spin a lot faster.
So what we need to do here to build our hurricane is to get the air spinning. And that's what this is for. So we've got a mesh here that when we start spinning it, will actually catch the air and make the air spin.
So we've got basically a cylindrical mesh around the fire. And as you can see, as the air starts to be spinning slowly by the mesh, as it gets into the centre, it spins really, really fast and forms this spinning column of air, which is actually getting a little bit high, and you might want to slow down, Ginny, before we hit the ceiling. And this is essentially working on the same principle as a hurricane. You do actually get fire tornadoes in large fires occasionally. If you get the air around a big forest fire spinning slightly, and the fire pulls it into the centre, you do get these much larger versions of this very, very scary spinning fire tornadoes.
Brilliant. Well done, Dave. Thank you, Dave and Ginny. Any questions about extremes of weather, extremes of hurricanes, or other questions about physics, chemistry for Dave and Ginny?
Hi, it's Aaron here from Hardwick. I was just wondering, has there ever been a real fire tornado in the scales that we have normal tornadoes in this world?
I haven't seen any really huge ones going up really high. I think it'd be difficult keeping the fuel burning. It's very, very large. They've definitely been sort of 50 metres high, I've seen pictures of, but that's not to say that I'm an expert on fire tornadoes globally, I'm afraid.
So, Dave, if you had a really big fire in a forest or something, could this cause the same sort of phenomenon? Could you get a sort of swirling effect like a hurricane? 'Cause it's creating lots of rising heat.
For that to work, you need the air to be spinning to start with. So you'd have to have some configuration of hills or something around it and a prevailing wind, which starts the air spinning a bit. Then the fire itself will kind of drag the air in and concentrate that spin and speed it up very fast, and you will get a fire tornado.
I'm Ewan from St Neots, and my question is, if there's a hurricane and you can't get away from it and you get sucked in, what would happen to you in the hurricane?
A hurricane is basically a really, really powerful storm. So in a hurricane, you can get picked up and thrown around. It can pick up cars and throw it around. When you're in the air, you're probably okay. When you hit the ground again, you're probably in trouble.
Or if you hit something else that's also being picked up and thrown around like a car.
Yeah, I mean, that's the other things which really can pick people up are tornadoes. And there's certainly been examples of parachutists dropping into, so not necessarily tornadoes, but places with a very, very, very strong updraft. And they end up going up and down and turn into a large hailstone, which is rather unpleasant.
So, Dave, what's going on in the eye of a hurricane? Why do we have an eye where it's really calm and quiet?
So essentially with a hurricane, air on the outside is spinning slowly. As it moves further and further inwards, for this effect, it's spinning faster and faster and faster, till you get a point in the middle whereby if that carried on going, it would be going at an infinite speed, and that doesn't work, physics breaks. So actually what happens in the middle is you get air sucked in from the top, and you get air coming downwards, at which point this is dry and it's not damp, so you get clear with no clouds on the top, and it's coming down and not spinning, so it's perfectly still.
It's Victoria from Cambridge. I was just wondering, what's the difference between a hurricane and a tornado?
A hurricane is one of these huge storms, hundreds of kilometres across, which is essentially working on exactly this principle. A tornado is a much, much smaller effect, and how it actually forms is a lot more complicated. To be honest, I haven't quite got my head around it. It's a lot more to do with winds in a much smaller space, and it's much more violent.
I think they begin as a very powerful draft running in one direction, which pulls another jet stream of air and puts a torque or a twist on it, which causes it to angle down. And so you've got a very tightly rotating column of air, which is then pointed down towards the ground and has this obviously devastating effect because it's a lot of force over a very small area on the ground.
Hi, it's Fergal from Cambridge. I just wondered why we always hear about severe tornadoes in the States, but not many reports of very fatal tornadoes from elsewhere in the world, where the climate, I assume, is similar.
Is it true that actually there are more tornadoes in England than there are in America? We just actually don't see the manifestations because they're quite minor.
I don't know. Is it true, Chris?
I've heard that. And am I alone? Has anyone else heard that? I'm sure that's a fact. James?
Yeah, we see there are lots of them in hot deserts, I know. I've seen many of them in Iran and in parts of the Middle East. They don't seem to get as big as they do in America. And anyway, they're in the desert, so who cares? They don't do very much. They make it very dusty, but they don't actually cause that much damage. The small versions are called dust devils. You see them as corkscrew things that's going across the countryside. If you happen to walk into one, you get covered in dust. But the scale is not very big.
You can experience that in Cambridge at certain times of the day. One over here.
Hi there, this is Mark again from St Neots. I'm actually Ewan's dad, and he was born up in the Highlands of Scotland. And when we were living there, when he was very young, we caught the tail end of Katrina, which still had quite an amazing, devastating effect. There were still upturned boats everywhere, roofs off of all kinds of things, roads into the sea. Do you know the different effect of hurricanes that are travelling over the sea or land, and how much that will affect how they decrease in their power or anything like that?
So hurricanes they get a lot of power from the hot water. So they tend to lose power as soon as they go on land because there isn't that hot water driving. Water vapor is less dense than normal air, so it floats upwards and that drives the circulation really strongly. When they get too far north, they also tend to get, because you get lots of high-speed winds high up, you tend to kind of blow the top off them a bit, and they also get weaker. So even though it was a strong storm when it was up here, and the sea underneath isn't as hot either. So as you go north, they weaken, and when they go over land for a long time, they weaken as well.
More kitchen science in a second. Meanwhile, thanks to Dave and to Ginny. You're listening to The Naked Scientists, and my name's Chris Smith, and we're live at the Cambridge Science Centre, where we are talking extreme geology this week. Our guests this evening, James Jackson, Tanuka Ilanko, and also Arwen Juice. They're all earth scientists. And Tanuka, you work on volcanoes. Tell us about what you do.
I'm a volcanologist working on volcanic gases, and most of my work is done on gases from Mount Erebus volcano in Antarctica. So what we do is set up an instrument on the crater of the volcano, and inside the crater there's an active lava lake. Now, these are quite unusual. An active lava lake is a sort of pond of lava, but for some reason it's connected to the source of the lava. And so there's fresh magma coming up, so the hot stuff is coming up and the lake is turning over. And all of this time it's emitting gases. Now the thing about these gases is they're always in the magma when the magma's at depth. It's a bit like a bottle of Coke. You've got no bubbles in it when it's sealed, as far as you can see. But there's carbon dioxide inside the bottle, and it's all dissolved because the bottle is sealed. When you open the bottle, you're letting some of the pressure out, and suddenly all of these bubbles start forming, and stuff comes out the top. It's the same thing inside a volcano. What we're trying to do is measure the gases and to find out where they come from and how that's driving the lava movement inside the volcano.
Quick practical question. Why Antarctica? I mean, I know you get to go to Antarctica, which I'd love to do, but does that not limit how often you can go there?
It does mean we can only go down there once a year, and this year we can't actually go down there at all because we're going with the US Antarctic program, and unfortunately things are shut down there.
They're closed for business at the
Yeah.
moment, aren't they? So that scuppered your expedition then?
But normally there's very good fieldwork support. And like I said, active lava lakes like the one at Erebus are quite unusual. So the opportunity to work there makes it worth the effort.
How big is this thing?
When I was last there, it was probably about 30 metres across, the lava lake itself. The volcano is nearly 4,000 metres high.
And how hot is that lava lake?
That's a good question, and it's one we've been trying to figure out, but approximately 1,000 degrees Celsius.
Wow, so you wouldn't last long if you took a dip?
No.
I mean, what does that do to the ice in the environment?
The crater itself, closest to the lava lake, is empty of ice, but around the volcano it's still covered in ice and snow.
And in terms of actually what this volcano is, volcanoes come in different flavours, don't they? So if we look in different parts of the world, they behave very differently from each other. What determines that, and what sort of flavour of volcano is Erebus?
So some of that is to do with sort of deeper part of the earth, so what's underneath the volcano, and to do with how the plates which are underneath the volcano are interacting, which maybe you might hear more about from Arwen. Erebus is quite a runny magma, relatively speaking, and so it's got this active lava lake. Some other volcanoes might be more explosive. They might get blocked up more easily, and you get bigger explosions.
And what are you learning from the gases?
The gases show some interesting patterns. So when we get big bubble burst explosions from the lava lake, they're often quite rich in carbon dioxide. Sometimes we see very cyclic changes in the gas coming out, and we're still trying to figure out what's causing that.
We're going to come to your questions in just a tick, so have your thinking caps on. I've got loads of emails on volcanoes here. So let's take the first one. This is from Dreamcatcher37 on Twitter, who says, how much effect does volcanic activity have on global warming? What's their pollution impact?
That's a very good question. One of the main things people say about volcanoes' impact on the climate is the sulfur dioxide that they output, and the fact that it can have the effect of masking the Earth from incoming radiation, and so actually promoting cooling.
Got an email here from Wim Spronk, who has actually said that if you look at history, there's evidence for some massive eruptions millions of years ago, which were covering, an area the size of North America with ash and things. And they go on to say, well, isn't there a massive hole left underground when all this stuff has come out?
I guess there would be, yeah.
Any questions?
Hello, I'm Jonathan from Cambridge. I understand the caldera under Yellowstone Park is quite dangerous. I mean, how dangerous is it? Is it likely to erupt at any time?
So that actually kind of flows on from the previous question. One of the things that can happen, and I think this will be demonstrated to you later, after a big eruption, is that a whole lot of the stuff that was underneath the volcano has somehow emptied out, and that leaves a space, which means the stuff on top can collapse in. So a caldera forms usually when a big magma chamber, the source of all the stuff that erupted, has emptied and left a space.
And if that thing goes off, what will be the effect?
Very big.
Bad. Any other questions?
Hi, Aaron from Hardwick here. Could you just sum up the gases that come up when volcano erupts?
So there can be a lot of different gases that come out. Most of what we see is water and carbon dioxide. Sulfur dioxide can be another big one. And then I could go on forever, but some of the other main ones are carbon monoxide, hydrogen chloride, hydrogen fluoride, H2S, which is the stuff that gives off the funny smell.
I've got two emails, one from Devin and one from Richard Roberts. They both emailed Chris at thenakedscientist.com. They say, do volcanoes cause global warming or global cooling?
That's another very good question, and I'm not sure it's one I can answer directly. The historical record of big eruptions, for example, there's a big eruption in Iceland called Laki in human history, and so we know that it had crazy effects on the climate in different parts of the world. What we tend to see is extremes of weather, but how that effect is felt in different places will vary.
James?
There's some well-known causes. There's one in 1811 or 1812 in Indonesia, and that created famously the year without a summer, which caused all the crops to fail in northeast United States, and which started the great migration to the west country, to Oregon and so on. And they didn't know at the time what caused it, but it was a massive eruption in Indonesia, producing a huge amount of dust in the upper atmosphere. And what that does is shield the atmosphere from sunlight, and it cools. The other one closer to modern times was in 1990 in Philippines. A big Mount Pinatubo exploded, and that reduced global temperature by 0.5 degree for 2 years. And that doesn't sound like much, 0.5 degree, until you realize that actually even in the last ice age, when the ice was maximum, the global temperature was only 4 degrees colder than it is today. So messing about with global temperature at a few degrees level is quite a dangerous thing to do. But mostly it's cooling that I know about from historical records.
Hi, I'm Ben from Cambridge. I was just wondering whether new volcanoes can form and how frequently that happens.
Depends on where you're looking. In some ways you can say that new volcanoes are forming all the time. Usually deep under the ocean, there are plates where the ground is moving apart, and these are called divergent plate margins. Along these you've got magma coming up, and I guess in a way you could call these volcanoes that are constantly forming. Volcanoes can always form. There was a famous case of a Mexican cornfield where this farmer looked out one day and saw a volcano starting to form.
Email from Brian Hauser, Tanuka, who says, how do islands get produced in the ocean? That's also often a volcanic phenomenon, isn't it?
That's right. And again, it's just a volcano forming, but they've been building up from the seafloor. So a lot of these volcanoes are much bigger than the ones we see on land, for example, in Hawaii.
Hi, I'm Brendan from Cambridge. How likely do you think we are to see another Pinatubo type eruption which cools the climate in sort of our lifetimes?
That's a good question, but it's not one I have an easy answer for. Unfortunately, forecasting of volcanic activity is still quite difficult.
It's really difficult to make predictions. It's very difficult to forecast earthquakes, and it's also very difficult to forecast volcanoes. at least with volcanoes, sometimes we have a little bit of warning. The volcanoes that are close to cities like Vesuvius are continuously monitored. And we hope that we will notice the vibrations, the small earthquakes that will start happening in the few days leading up to the volcanic eruption. So hopefully, with volcanoes, we'll have a little bit of warning. The question is, will we be able to evacuate people? Is it possible to actually evacuate a city like Naples in just a few days? I'm not sure. It's a very massive city. Earthquakes is a completely different story. I'm not sure we'll be able to predict those. The only thing we might be able to do is get a feeling for how big the earthquake will be once it has started. There's work being done in the United States, and if you would know after you've just felt the first few shakings, if you have a computer program that can then say, this is just going to be a small earthquake, no worries, or this is going to be a big one, then the really destructive waves will come maybe 20 seconds later. You will have 20 seconds to do some important things, maybe turn on some emergency equipment, warn people that they can just move from where if they're in a more dangerous place, go and be in a more safer place. That will not be a proper prediction days in advance, but it might give us a little bit of extra safety and just prevent some of the major disasters happening, potentially killing slightly less people than what's happening nowadays.
This is Fergal from Cambridge. I wonder if it's possible to tell from the nature of the volcanic gases what their original origin is, if they're from some chemical reactions with the geology, or if they can be traced somehow back to atmospheric gases way back in geological history, or perhaps groundwater.
So some of the work I'm doing is trying to model where the gases I measure came from, but just within the volcano. So some of this is to do with how soluble a gas is, so how much it wants to be dissolved inside the magma. And some gases like water are quite soluble. Other gases like carbon dioxide aren't. So it might not be that unusual for a volcano to be emitting carbon dioxide, even though nothing is about to happen. But when you start seeing, for example, a lot of sulfur dioxide coming out, that can be a warning sign that the magma has reached a higher level in the volcano. So a more soluble gas like sulfur dioxide that usually likes staying dissolved has depressurized. So the stuff that's keeping it dissolved inside the magma has lessened, and it's also starting to come out, and that can be a warning sign of an eruption.
Tanuka Elanco, thank you very much. Okay, time for the people sitting at the front to get very afraid, because they made a flame tornado. Now they're going to make a volcano. Dave and Ginny.
Right, so we've been talking a bit about calderas and how volcanoes get that really distinctive shape. I mean, if anyone says the word volcano, I think most of us get this image in our mind of quite a steep mountain with this big crater in the top with bubbling magma inside. But why are they that shape? Well, it's all down to the physics, and we're going to try and recreate that now.
So this isn't all volcanoes, but we're explaining that kind of classical volcano. So Tanuka was talking about the thing which has triggered the volcano is a load of magma inside. It's all under pressure with lots of gases in there. So I'm going to model that with a balloon, which I'm just going to blow up now.
Okay, so Dave's going to blow up the balloon, and that's the equivalent of the gases.
And the magma. In theory, it should be hot and at several thousand degrees centigrade.
We thought that would be a bit dangerous, so we're going to stick with a cold balloon for now. Okay, so we've got our chamber full of magma and gases, and it's all under pressure, so it's not going anywhere. But that's surrounded by rock, so we're going to use flour to model that.
So this is basically stuff which has been erupted in previous eruptions, forming a nice sort of mountain shape and an awful lot of mess. So that's one bag of flour.
You can say it's, at least you can say it's ground.
We're not sure we're going to have enough flour here, so you've now got flour all over your face. Always good in an experiment if you end up covered in it. Depends what the experiment is. We're going to carry on building our mountain around our chamber of magma, and we've got to cover it up completely. So now this is before it's erupted. So we've got our nice little mountain there. Now, Tanuka, can you come and give us a hand with this?
I feel the volcanologist ought to trigger the eruption. So Tanuka's going to take a pair of scissors and go in and try and cut the top off that balloon.
Okay, so that wasn't quite as dramatic an explosion as some volcanoes. But what you might be able to see is that we've got a sort of crater that's formed. So where the balloon was, the flour has all fallen in on itself and it's formed a crater. And is that actually how it happens with real volcanoes?
Well, real volcanoes don't have balloons inside them, but they do have magma and gas that's under high pressure. And when, for whatever reason, it's able to come up and some of that pressure is released. Part of the cool thing about this experiment is that it shows a couple of things. You probably wouldn't have been able to see it, but as the air came out of the balloon, it sort of hollowed out some of the top of the flower volcano. So when you have a lot of gas or magma escaping at high energy, it can excavate a little bit of space around the crater. The other thing you see is that as the balloon deflates, you end up with an empty space, and that collapses in on itself. There's no pressure pushing out on the volcano to hold the sides up, and so it all collapses.
Thank you very much.
So any questions for Dave or Ginny about flower volcanoes?
I'm Ewan from St Neots, and my question is, if a volcano erupted on an island with mainly the volcano, how would it devastate the people on the island?
So there are a lot of different effects that a volcanic eruption can have on people. Some of the most damaging eruptions are those that send a lot of ash and gas all mixed up in a very fast, turbulent flow down the side of the volcano. These are called pyroclastic flows. These can be hot, they can be very fast, they're very powerful, and some of the biggest losses of life have been as a result of these.
And you can also get, some of these gases can be quite poisonous. So wasn't there huge problems in Iceland a few hundred years ago when lots and lots of hydrogen fluoride was given out, and a large proportion of the Icelanders died because of these poisonous gases which got kicked out?
Yeah, so there was this Laki Fisher eruption which went on for a long time. And the thing with these acid gases is that they can also damage the environment. So there was a lot of crop failure, a lot of livestock that died.
You're listening to The Naked Scientist, recorded live at the Cambridge Science Centre. I'm Chris Smith, and we are talking extreme geology this week, as well as a whole bunch of kitchen science experiments with Dave Ansell and Ginny Smith. We have three esteemed guests from the Department of Earth Sciences at Cambridge University: James Jackson, Tanuka Ilanko, and Arwin Juice, who, you're a seismologist, so let's shake up the world of geology a bit and tell us what you do.
Right, well, we've heard about earthquakes and volcanoes from the other two people here. That's the main thing you'll see, the main thing you'll hear about on the news. But all these things that happen at the surface of the Earth, they're driven by processes deeper in our planet. And if we want to understand them, then we need to know what's happening in the deeper parts of the Earth. And the way we look at that is by using seismic waves. So we can look at the earthquake itself, but these earthquakes, they generate waves. They travel all the way through the Earth. They don't only travel along the surface, they go right through its center. So an earthquake that would happen in New Zealand, we can pick that up here in the UK. We wouldn't feel it as human beings, but our seismometers, the very sensitive instruments that can feel these waves, they make recordings of those. So we can make pictures of what the deeper parts of our planet looks like. And it's a very, very nice way to understand the tectonics, the movement of plates, the generation of earthquakes, the reasons why there are volcanoes in some places. We can link those to the deeper parts of our planet. And we make pictures just like making a brain scan, and our pictures look very similar. Give them colors, red and blue. They relate to regions in the Earth where the velocity is slightly higher or slightly lower. And we think we can link those to regions in the Earth where the temperature is slightly higher or slightly lower. Now, volcanoes, they need higher temperatures, and we would see them in our models. Places where the temperature is probably higher, that might lead to a volcano at the surface of the Earth. What we can also see is places where the velocity is slightly faster and the temperature is slightly lower. And that's probably places where plates, we just heard about how we have in the middle of the oceans, different plates, new plates being generated. We have volcanic eruptions and we generate new parts at the surface of the Earth. If we generate new parts, all the volcanism, we need a place where that's being compensated. We need to destroy these new plates. And those are called subduction zones. And a very important place where we have a subduction zone is on the Japan, probably being the cause of the big earthquake that happened and caused a tsunami.
Arwin, I've got an email here from Tony who says, if we were to cut the Earth across and look inside and draw a sort of map, what is the structure of the Earth?
The Earth mainly consists of a few big layers. It's like the different layers of an onion. The top layer is about 3,000 kilometers thick. We call that the mantle. That's where all the excitement is happening that will relate to the tectonics there. Then we go below that, we get the core, and that's a very, very hot region made of fluid, iron, and nickel. It's fluid, and inside there is a very small region of about 1,000 kilometers thick, which is the solid inner core. So there are mainly 3 big layers: a solid mantle, a fluid outer core, and then a solid inner core again.
How do we know what's in those things? Because you've said there's this iron in there, but no one could go there. So how do we know there's iron in there?
It's a very good question. We cannot go there, but we have an idea of what the average composition of a planet is. We can look at meteorites, and we have a feeling what the average composition is of things that get formed in the solar system. And we know those must contain a lot of silicon, but also a lot of iron. And when you form a planet, the iron is very heavy, and it will sink towards the center of the planet, forming a core, and the lighter elements like silicon will stay in the outer part, the mantle.
Because I've got an email here, someone saying, what would happen at the core of the Earth? Because if all the heavy stuff sinks, and we know that gravity is attracting everything to itself, then at the very centre, there should be no net gravitational effect. So wouldn't the core actually be hollow?
Well, there's also a pressure effect. So we have incredible pressures deeper in the Earth. So it wouldn't be possible to sustain a hollow anywhere deeper in the Earth. So no, we don't have a hollow at the centre. We have a proper solid inner core and no hollow part there.
And Jan says by email, what keeps the Earth's core hot?
Well, a lot of the heat has just been there since the generation of the Earth. It's heat that's still remaining there from when we generated our planet. The planet is very hot, and it's just still slowly cooling down. On top of that, there's probably some radioactive decay, which will also generate heat. So there are different processes happening, but the main heat that's coming out is also, because I said there is a fluid outer core and a solid inner core. That solid inner core is slowly solidifying, so it's growing and growing, getting bigger over time. And when it solidifies, that releases more of the heat, which makes the rest of the core very hot.
And on the surface of the Earth, it's carved up into plates, and we have continents. If we look on any other planet in the solar system, do they also have tectonics like that, or are we unique?
We have other planets that are a little bit similar to the Earth, and we can see some evidence of tectonics on those other planets, although the real way to find out would actually to go there and see, can we measure any quakes on those different planets?
After you.
Yes. But if you look at Mars, for example, we do think there might have been, or there might still be, plate tectonics there, and another planet that people have been looking at is Venus. They're very different to Earth, though, and the things that are happening, the processes that might be happening deeper in those planets are probably quite different. And the interesting thing will be to send seismometers to these planets. That would be very impossible probably for Venus, but it will be possible for Mars, and there's some plans to send seismometers there, and hopefully then we'll be able to study better if there's any plate tectonics there.
Let's take some questions.
Hi, I'm Chris from Cambridge. The information that you collect following an earthquake, does that help you build up a picture of where is the best place on the Earth that you can harness geothermal energy like they do in Iceland?
I think we know pretty well which are good places to harness geothermal energy, and it's a beautiful thing. When you go to Iceland, yes, there is hot water, and we don't need to burn any fossil fuels for that. I think we know the geology at the surface well enough to find those places, but if for whatever reason we wouldn't, yes, we might probably find that there are places with small vibrations which would be related to the volcanic activity and would be places to harness geothermal energy.
Hi, David from Bury St Edmunds. What sort of resolution does your seismographic mapping technique give?
It depends on the seismic waves you use for looking at the data, and it also depends on how deep you want to look into the Earth. Near the surface, we can have a very good resolution, and we look at data that travels really fast, and the waves oscillate really fast as well. They will oscillate maybe at a second. That means that the wave going up and down only takes a second. Then we can have resolution of a few kilometers. The deeper you go in the Earth, the less and less resolution you have, and you're looking at hundreds kilometers, and at the deepest part, it's almost 1,000 kilometers. So you have a wide range of resolutions.
I've got 2 emails on almost the same question. So John Stenson and also Delicia, they would like to know what provides the energy that keeps the plates moving, and why do tectonic plates drift around? Because I think the statistic is they move at roughly the same rate my fingernails grow. Is that right?
They
or
do.
Faster?
Yes, they do. Now, most of the heat comes from the core, the latent heat of the core. So that needs to go somewhere. So it's in the core, and it gets into the mantle, which is cooling down. And you get at the top, you get a surface, which is like a crust. You would have, if you're cooling down some milk, you get a crust on top of it as well. And that's moving, adjusting to it. We don't really think that actually moves the plates. That's probably a separate system. But they are moving at speeds similar to the speed your fingernails grow with. And we know it keeps itself going. So we can determine what the powers are of the forces that will be building the new plates and how they're being dragged down. But how we would actually generate the plate tectonics from the motions deeper in the planet is something we just don't fully understand yet.
Hi, it's Pete from Cambridge. Can you explain what causes the Earth to have a magnetic field and why it sort of switches over geological time?
Yes, that's a very good question. Yes, you're right. The Earth has a magnetic field. And when you look at it from the outside, it looks like a bar magnet, which you've been playing with as a kid probably. However, in the Earth, it's not a bar magnet. It's actually generated not by the solid inner core, but by the fluid outer core. There are motions, and because it's at such high temperature, these motions, they generate the magnetic field. We call it the geodynamo. We don't fully understand how to do that. We try to do this with computer calculations, but it's such an extreme environment that we cannot do it yet with computer calculations. Some people try to do it in the lab as well. And again, you cannot get iron at such high pressures and temperatures in a lab. So people are looking at sulfur experiments. So it's the outer core that's generating the magnetic field. We can understand that it will flip at irregular intervals. Again, how that's all exactly happening, it's something we're still trying to learn about.
And James, the fact that we've got a magnetic field and that field gets written into rocks when they're deposited on the ocean floor is actually one of the reasons why we now know about the movement of tectonic plates, isn't it? Wasn't that some American geological surveys that showed that?
No, it wasn't. It was people in Cambridge who showed that, famously.
Let me
in 1964, two people in our department.
Wasn't that some august Cambridge?
Yes, you're quite right. It was some people in my department who discovered that in 1964. It was very clearly their discovery. What actually happens is because of the magnetic field, as we've heard, magma comes out of volcanoes in the middle of the oceans, and as that magma cools and makes rock, it has a lot of iron in, and the iron gets magnetized in the direction of the Earth's magnetic field at that time. So if you can imagine a conveyor belt coming out of the middle of the ocean, it's like a tape recorder. It gets magnetized in stripes as it comes out. These stripes are either in the orientation of today's field, or, as someone said in the audience, the field flips and it looked like the reversed. But basically, the ocean is just a mass of stripes of magnetized rock. And you can, if you can see that that's how it's formed, you can wind it back the other way, if you like, and see how all the continents move around. The continents are just passengers on this conveyor belt. So if you can rewind the conveyor belt, you take the continents with you, and that's how you can make jigsaw maps of how the continents all fit together.
Vanessa Penman got in touch by email and says, what's actually the consequence of Earth's magnetic field reversing?
It wouldn't be very nice to experience it, especially nowadays. We really depend on our magnetic field for a lot of different things. It flips, and it doesn't flip instantaneously. It can take up to a few hundred, maybe even 1,000 years. And what first happens is that the magnetic field gets less and less and less strong. That wouldn't be so nice because we need the magnetic field. It protects us against solar radiation. We use it for navigation, birds use it. So I think it would be quite difficult to imagine what will happen when the magnetic field flips. And the problem is we don't really know when it will happen. It happens at irregular intervals. It can be millions of years before we get one, and it can be just tomorrow.
Hi, I'm Simon from Cambridge. We know that the inner core is a solid structure, but with all that heat surrounding it, how do we know that it's solid, and why is it solid?
Well, we know it's solid because we use these really, really big oscillations. If you have a big earthquake, the whole Earth will ring like a bell. The whole Earth will slowly expand and contract, and this will take days to continue. Now, we can listen to or look at all the different tones, as you would say, if you see this as a musical instrument, and all these different measurements we can make. And if you want to explain them, there's only one way to do it, and that's with a calculation in which we let the inner core be solid. If we allow the inner core to be fluid, we cannot explain the data that we measure after these big earthquakes.
Arwen Juice. Okay, some more experiments. Dave and Ginny.
Who knows what this is? Anyone eaten one of these before? No? No one's ever had... Oh, yeah, there's a couple over there. So we've got a red cabbage here. Now, you might wonder what that's got to do with extreme Earth. Well, red cabbage actually has something in it which can act as a pH indicator. So it can tell you whether things are acid or whether they're alkaline. Now that relates back to earlier when Tanuka was talking about what comes out of volcanoes. As well as the lava, you get all these different gases. And some of those gases can go up into the atmosphere and they can actually cause acid rain.
Although what we're going to be using here isn't really a major part of acid rain at the moment. So what we're going to do is we're going to take some water and see what happens to it if you add one of the big gases, which Nick was talking about, is carbon dioxide. And there's also a gas we're pumping into the atmosphere all the time as we drive around in our cars and run our power stations. So what I've done is I've taken this cabbage and I spent about an hour with Tom at the back there mashing it, and then I kind of squeeze water into it, and I've made a nice bottle full of cabbage juice.
Just what you want for your dinner. Nice bottle of cabbage juice. It's a beautiful purple colour, actually. I think you could probably market that.
Does it taste nice? Have you drunk it?
It tastes of cabbage. If you like raw cabbage, then this is obviously the drink for you. So there's a slightly bluish tinge to it because Cambridge water has got lots of dissolved chalk in it, so it's slightly alkaline. And what I've got here is a device for dissolving lots of carbon dioxide in water.
So when you buy a fizzy drink, that's made fizzy because they've dissolved a load of carbon dioxide inside it. It's kept at quite high pressure in the bottle, and then when you open the bottle, the pressure's released, the bubbles can come out, and you get your lovely fizzy drink. But this is a machine designed to make drinks fizzy.
So basically what it's going to do is inject high pressure carbon dioxide into the water. Do you want to volunteer? Does anyone want to do the injection? Ooh, do you want to come up?
Round of applause for our volunteer, please. What's your name?
I'm Minnie.
Brilliant. Okay, so what are we going to get her to do?
So Millie, if you just press the button there, and if everyone else watches what happens to the colour of the liquid, go for it.
That was a slightly rude sounding noise.
Try again. That'll do. So has anyone noticed a change in colour?
So what's happened, Millie? Can you see what colour it's gone?
It looks the same to me.
She was behind when it was happening.
Let's try that again.
Can we put a bit more through?
A bit more in.
Have a watch while Dave puts some more in. So you should be able to see that it started going slightly more pink in colour. It was quite a bluey purple, and it's now quite a sort of pinky purple. Brilliant. Thanks a lot, Millie. You can take this through again.
So this means that if you dissolve carbon dioxide in water, it becomes acidic, because pink cabbage juice means it's turned into an acid. This is quite important because it's what creates caves. So you dissolve carbon dioxide in water, that makes it slightly acidic, and it will dissolve the limestone and dissolve out sort of tunnels in the rock where water's flowing and make caves. It could also be a big problem with the carbon dioxide we're pumping into the atmosphere, because it's actually going to make the sea more acidic, which makes it much harder for creatures with shells in them to grow a shell, because there's all this acidic acid in there trying to dissolve its shell off all the time. So it could cause all sorts of problems for the oceans.
And when we have volcanoes releasing things like sulfur dioxide, which will do a similar thing, they'll dissolve in water but form a much stronger acid, then we can get the acid rain that you may have heard of that dissolves buildings and statues and that sort of thing.
Ginny, thank you very much.
And if anyone wants any fizzy cabbage juice, we've got some here.
That's the next experiment, to drink it and see what happens. Any questions?
I'm Ed from a town called Swavesey, and I was just wondering if there's ever been such bad acid rain to kill anybody or badly injure anybody.
Not that I've heard of. I think the concentrations that you get in acid rain are low enough that it doesn't tend to.
I guess the one time when it might produce something nasty is if it had come out of a volcano, which is why I'm looking over at the volcanologists over there. If you've got lots of nasty gases coming out of there.
The gases themselves can definitely be harmful, and the acid rain can also be very damaging to the environment. I'm not sure if there have been any cases of someone being directly killed by acid rain.
I think it's more likely to cause damage if you inhale the gases and they actually get inside you, rather than once it's dissolved in the rain, it's kind of diluted a bit, so it's not going to be as dangerous.
And the reason why they're actually really quite dangerous is they create essentially an acid inside your lungs, and then that attacks your lungs, these gases. So carbon dioxide's fine, but things like sulfur dioxide can do really nasty things to your lungs.
Tanuki, you do get situations where you get lots of gas dissolved in a lake, for example. We've heard of examples where lakes suddenly burp up a huge load of, say, carbon dioxide, and it will then engulf a local populace, and people drown effectively in CO2, don't they?
There was a case of this, I think it was in Lake Neos in Cameroon, where a lake overturned and a whole lot of carbon dioxide that had been inside it came out and killed everyone overnight.
Oh, and I've got an email over here from someone called B.R. Shorten. It refers to a story a few years ago about an earthquake in Italy where a whole bunch of toads disappeared before the earthquake happened. And these toads always congregate when there's a full moon to mate at a certain time of year. And there's evidence showing that they began to congregate, but then a little bit before the earthquake struck, they all vanished inexplicably. And it wasn't until the last aftershocks had passed that they began to come back. Do you think there's any possibility that there could be something going on that these creatures are tuning into?
Perhaps. It's really difficult to predict earthquakes. And yes, there have been anecdotal stories about animals responding to it, like the toads. Will it be really useful for us to predict an earthquake? That's another issue. Because if you want to predict an earthquake, you want to be very sure that that earthquake is going to happen. And it's difficult to watch the toads. They might be moving away for some other reason. And then you have evacuated the whole city. The earthquake didn't happen. People will get very upset. They'll get back to their houses. The earthquake might be 2 days later, but they're back. They won't listen to you anymore. I think it's a very difficult business. So yes, they might have some sensitivity to some vibrations, but how that is really working, very unclear and not a very safe way to predict an earthquake.
Hey, I'm Ben from Cambridge, and I was just wondering, you were talking about acid rain dissolving statues. Is this an intermediate threat at the moment, or is it in the future?
So that has actually happened. There are places in America where they have taken to covering over their statues during the winter to stop that from happening. And it's the same thing. If you've ever looked in your kettle, there's a kind of scum, sort of almost like bits of rock in the bottom, and that's calcium carbonate. And what's happened is that has come out of the water that it had been dissolved in. What's happening with the statues is kind of the opposite. When the rain's acidic, it can dissolve that calcium carbonate, which is limestone, which a lot of stuff's built out of, and that can really wear away statues.
It was a big problem sort of 20, 30 years ago, but people have run power stations and people and cars and things with a lot of effort into especially removing sulphur. So that was one of the big things which made acid rain. They scrub it out of the chimneys of the power stations and they actually extract it out of things like diesel, so it's not actually in the fuel which you put in your car. So certainly in Europe, it's much less of a problem. I imagine it's still a problem in China because they're less far on in the cleaning up states than we are.
Hi, Aaron from Hardwick here. My question is, would you say that acid rain's main cause is from volcanoes or inefficient car engines?
Well, as we were just saying, it definitely used to be power stations when they were burning coal and just chucking it all out. And, you know, you hear about the London pea super smog and it was really awful, the kind of emissions. Then I would say it would definitely have been that. Now we're cleaning things up a bit more. I'm not sure. Do you have an opinion?
I'm not sure either, but I suspect industrial causes are a bigger factor. With volcanic eruptions, generally, if you have a big volcanic eruption, you have a lot of other things to worry about. Acid rain probably isn't the immediate priority. And even with things like hydrogen fluoride coming out of a volcano, for example, in the case of Iceland that I mentioned earlier, this big Laki eruption that lasted a long time, the fluorine caused poisoning of crops and of the cows. That's not necessarily caused by the rain, it's caused by the fluorine. So among all the other things you have to worry about, I think acid rain from volcanoes is lower on the priority list.
Hi, it's Ewan from St Neots. My question is, if acid rain were to fall on a lake, what would be the case that would happen?
Well, if a lake becomes too acidic, then it can be really bad for the fish living there. If it becomes too acidic, they can't survive. And for any other creatures living in the lake, it's not good. But it depends how big your lake is, because if you've just got a small amount of acid rain going into a big lake, it's not going to be very acidic overall.
It was one of the things which caused everyone to clean up their power stations in Europe. There were a lot of lakes in Norway and I think particularly Norway and Sweden which were getting poisoned because of it. But I think they've got a lot better since we stopped pumping out lots of acidic gases from our power stations.
Jeannie and Dave, thank you very much. Okay, we have run out of time, and so I have to ask you, please join me in thanking an amazing panel of people, James Jackson, Tanuka Ilanko, and also Arwen Juice, our kitchen scientists, Ginny Smith and Dave Ansell, and on the sound, Dominic Ford. You've been listening to The Naked Scientist, recorded live here at the Cambridge Science Centre. We're back next month with another one of these live at the Cambridge Science Centre events. The Naked Scientist comes to you from Cambridge University. It's supported by the Wellcome Trust and also by the EPSRC. My name's Chris Smith, and thank you very much for listening. Goodbye.